Hi and welcome to this quick review of phenols, which will focus on the reasons behind phenols' additional reactivity over and above benzene and specific reactions as a functional group in its own right. The clip will assume at all times that you've got your independent study and notes completed in front of you and is designed to reinforce what you've looked at already. So a phenol is any compound which contains a benzene ring with an OH group or hydroxyl group directly bonded to the ring. So the carbon atom on the benzene ring where the OH group is attached automatically gets assigned carbon number 1 when naming. So if we highlight the phenol functional group in our substituted phenols here in pink, we can also number the carbons so you can see where the naming comes from. As you can see, the carbon where the OH group is attached becomes carbon number 1. So these molecules are not phenols, but they are aromatic alcohols, and their chemical and physical properties will mirror those of other aliphatic alcohols. So these compounds are not phenols because the OH group, as you can clearly see, is not directly attached to the benzene ring, but they're still considered as aromatic alcohols because of the presence of an OH group. So their behaviour is going to be exactly the same as their aliphatic alcohol counterparts. But the benzene ring part of the molecule will keep hold of its normal chemical stability and reactions. So looking at some examples of the uses of phenols, 2,4,6-trichlorophenol, or TCP for short, was discovered by a British surgeon called Joseph Lister in 1870. And because it's an antiseptic, its discovery obviously revolutionised surgery at the time. And Listerine mouthwash that you can buy in the pharmacies and shops nowadays is named after him. But the problem was that we also discovered that some phenols can be quite corrosive to healthy tissue as well as being able to kill bacteria. So they've been superseded by other antiseptics in this field. So this is another example of a phenol, but have a look at the name, it's quite interesting. It hasn't got phenol in the name. So because of the carboxylic acid group being slightly more reactive than the phenol part of the molecule, the name is dominated by the carboxylic acid, so hence why it's called 2-hydroxybenzoic acid. So although the hydroxyl group is still part of a phenol functional group, the carbon atom on the benzene ring where the most reactive functional group is attached becomes carbon number 1. So let's look at the bonding in phenol. So it's based on the same delocalized pi system model that we use for benzene. So if we draw out a normal benzene ring but substitute one of the hydrogens for an OH group in the normal way, including the correct bond angle of 104.5 degrees around the COH bond, you can see that there's 2 lone pairs on the oxygen. So as well as the sideways overlaps of the p orbitals in the carbon atoms, one of the lone pairs on an oxygen, also in a p orbital, is delocalized into the pi system by p orbital sideways overlap between carbon and oxygen atoms. So this has the effect of increasing the electron density within the delocalized pi system to 8 electrons instead of the usual 6 that you find in benzene. So this additional electron density that you find in phenols has the effect of making them more able to attract electrophiles or induce dipoles. So therefore phenols are more reactive than benzene. Now the mechanism is still electrophilic substitution, but it just happens more easily with phenols than it does with benzene. So the bromination of phenol can be carried out at room temperature with no halogen carrier in the presence of aqueous bromine water, and you get 2,4,6-tribromophenol. Now obviously because the bromine substitutes for hydrogen, they have to go somewhere. So you get 3 HBRs. I've used up 6 bromine atoms. 3 have gone onto the phenol benzene ring and 3 have ended up as HBr. So therefore we need to make sure we balance the equation. So in structural form, I've put the reactants and products in blue, bottom right of the screen. And likewise with the nitration of phenol, you can use straightforward HNO3 aqueous. You don't need a nitrating mixture like you do with benzene, no refluxing, anything like that. No catalyst, room temperature and HNO3. And a general equation for both of the two products, you get a mixture of them, is at the bottom left-hand corner of the screen in blue. And it's important to remember that you get a mixture of 2 nitrated phenols, 2 nitrophenol and 4 nitrophenol. So phenol can also act as a weak acid. So if we go back briefly to the bonding in phenol, you remember that it's got additional electron density from the lone pair on the oxygen delocalized in the pi system. This makes the phenoxide ion more stable than would otherwise be expected. So metals and their hydroxides can both react with phenol to make phenoxide salts. In this case, we're making sodium phenoxide. But phenol isn't a strong enough acid to react with carbonates. So therefore this gives us an important test for phenols. So what happens is we watch out for the fizz of carbon dioxide gas. And we find that carboxylic acids will effervesce when carbonate is added, but phenols won't. And this means that the carboxylic acids are stronger acids, therefore, than phenol. So finally, to round things up, it's important to spend a little bit of time having a look at the relative reactivities of cyclohexene, benzene and phenol, because quite often you'll get long answer questions on these. So looking at cyclohexene first of all, as you probably recall, the high electron density in the carbon-carbon double bond attracts electrophiles and reduces dipoles. So this increases cyclohexene's reactivity to electrophiles compared to that of benzene. And the reaction proceeds via an electrophilic addition mechanism. So with benzene you've got low electron density by comparison within the delocalized pi system. And because of this, dipoles are not induced easily and electrophiles are not attracted to the ring easily either. So this makes benzene relatively unreactive, and therefore any reaction does proceed by the electrophilic substitution mechanism. This avoids disrupting the stability of the ring's pi system. So with phenol, you get additional electron density afforded by the incorporation of the lone pair on oxygen into the delocalized pi system. So this means 8 electrons as opposed to 6 electrons as you'd find in benzene. So this means phenol is more able to induce dipoles or attract electrophiles, which causes greater reactivity. But the reaction still proceeds by electrophilic substitution. It doesn't suddenly switch to electrophilic addition. It's still electrophilic substitution. So to summarise, let's quickly go through what you need to talk about to get the marks on these types of exam questions. You need to compare the relative electron density of all 3 compounds, how the electron density affects the reactivity, is it more or less reactive, and also why this is, e.g. the ability to induce dipoles or attract electrophiles. And although the question might not ask for a diagram, it's always a good idea to be able to put one in and label it to make sure that it's clear what you're trying to say. So why not now try and find some of these questions either in your textbook or in maybe a past paper exam and give them a go. So obviously practice makes perfect, but until next time, thanks for your listening and see you soon.